In Lecture 9, we took the time to explore the different types of reactions that coordination chemistry or coordination compounds can go through. They include associative reactions, dissociative reactions, different types of oxidation-reduction reactions. Today, we're going to look at the mechanistic studies behind substitution reactions. Do most substitution reactions occur through the associative mechanism or the dissociative mechanism? I want you to finish reading Chapter 5, and I want you to consider all these questions for your homework. They will help you prepare for your exam, and as soon as I receive your answers, I will post a key on the internet so that you can study for your quiz. Now, when we try to decide whether a chemical reaction occurs through associative mechanism or a dissociative mechanism, it can be very difficult. The reason why is associated with the rate determining step. In the dissociative mechanism, a 6-coordinate compound has to lose one ligand to form a 5-coordinate compound. That is the rate determining step. If you write a rate law for this, the rate law is just the rate is equal to the rate constant, which tells how fast this reaction is going, times the concentration of the reactant, ml6. For the associative mechanism, a coordination compound with a coordination number equal to 6 reacts with something like a solvent molecule, water, and forms a compound with a coordination number equal to 7. If we write the rate law for this reaction, the rate is equal to the rate constant times the concentration of water, which is one of the reactants, times ml6. Soon you will see that the rate law can be simplified to rate equals K times the concentration of ml6 for the associative mechanism as well. Notice that the rate law for each mechanism is identical. So, we need to determine which mechanism best explains substitution reactions. The following evidence can be used to support one mechanism type over the other. The first experiment that we will look at is the exchange of similar ligands, where one type has a different isotope of a certain atom. For example, we could look at the exchange of water with oxygen 16 with water that has an oxygen 18 on it. The second type of reaction that we will look at that will help us determine which mechanism is correct is anation reactions, where an anion replaces another ligand in a complex. The third type is aquation reactions, where a water molecule replaces another ligand in a complex. The associative mechanism is what we will look at first. For the associative mechanism, the rate determining step is the reaction between the solvent molecule and the coordination compound. Now, in pure water, the concentration of H2O is very large. It's 55.6 molar. Since there's so many water molecules around in solution, the likely collision that will start the reaction is between water and ml6. Since the concentration of water is so large, it will not change significantly during the reaction. This leads to the idea of pseudo first-order kinetics. Since water is relatively constant during the reaction, the concentration does not change. Its concentration becomes part of the rate constant. This is known as pseudo-first-order kinetics. For the associative mechanism, the rate is equal to the rate constant K prime times the concentration of water times ml6. Since the concentration of water does not change, many times it's included as part of the rate constant. So the rate law simplifies to rate is equal to K times ml6. The reaction rate appears to be first order, even though if you change the concentration of water, there will be a change in the rate of the reaction. This dependence on the water concentration is masked by its very large concentration in solution. So that makes it difficult to determine if an equation reaction, a substitution reaction, goes through an associative or a dissociative mechanism. So the experimental differences between D, which is dissociative, and A, which is associative, it really can be thought of in three ways. The pseudo first order rate law for the associative mechanism makes it very difficult to distinguish between the dissociative pathway and associative pathway. So which mechanism is preferred, dissociative or associative? Commonly, radio-labeled water is used to differentiate between the two types of mechanisms. Let the star beside the oxygen in H2O, whenever you see that, that will represent oxygen 18. So, which mechanism is preferred, dissociative or associative? The reaction we are looking at is taking a metal cation coordinated to 6 waters that are not radio-labeled. We introduce a small concentration of radio-labeled water and measure the rate of the reaction to determine how quickly the radio-labeled water is added to the coordination compound. Experimentally, this reaction is first order overall. That means it only depends upon the concentration of the coordination compound. However, this does not definitively suggest a dissociative mechanism over an associative one, because you could be looking at pseudo first order kinetics for a dissociative reaction. Examination of this reaction type as a function of different types of metal cations has many interesting trends.